Good afternoon, dear colleagues. It's our pleasure to meet you. Our course project is a joint project with a deep learning course devoted to image processing in the field of mobile microscopy. Next. Mobile microscopy is a technology where smartphone camera and its computational resources are applied for microimaging tasks with cheap optics and equipment. Significant decreasing of cost and rational usage of available resources allows to apply such technology in the wide range of cases, from mass screening to disease diagnostics in developing regions, where usually a lack of medical support is observed. Next. In the last decade, a huge step was done in the direction of creating different constructions of mobile microscope. A huge class in that area is formed by different lenses application, trying to provide the most universal one. That approach is the most affordable, and a lot of projects can be found both in scientific and commercial fields. Next. Another class of mobile microscopy technology is to use more sophisticated external devices similar to original microscopes. Researchers propose different constructions and modalities. This class of microscopes is much more suitable for different disease detections, easy to set up and tune focal length. Next. In 2015, there was an interesting experiment that demonstrates that quality of the smartphone camera in the research was taken iPhone the 4th, and we can see its measurements as crosses in the plot is good enough and comparable with the scientific equipment, which is marked as squares in the plot. Next. Such high quality of imaging allows to demonstrate relevance of the mobile microscopy application in many diseases important for humanity. They are presented as mass diseases like malaria and tuberculosis in developing countries, where fast and cheap diagnostic with the mobile microscopy may help a lot, as well as different cancer diseases. The field where timely diagnostics may save a lot of lives. Next. Also, there is a set of works with the concepts of mobile microscope usage as a fast, cheap, location, and most important, knowledge-independent system, where a smartphone is used as a capturing device that sends data into the cloud, where all calculations are done, and results and recommendations are sent back to the smartphone. Next. In the last decade, a significant step was done in the field of creation mobile microscopy devices. Also, some works demonstrated real-life problems application of that technology. But the problems and tasks remained the same as in the common microscopy, and even become more difficult because of cheaper optics and a lot of visual artifacts. In our work, we are focused on different techniques that might significantly increase quality of the obtained data from the mobile microscope. Next. In our work, we can see the data set, a very unique one, obtained from mobile microscope from the third-party company. The microscope is an auto-scanning device with several levels of scanning speed and is based on the wide field technology. All data was obtained from the Nexus 6P smartphone, which is in the middle smartphone class and quite affordable. The data consists of approximately 150 specimens video recorded with a different speed of scanning. So, Michael, could you continue, please, with our solutions?
Okay. Well, as said above, we have 3 problems, and our solution that we called Mobile Microscopy Deep Framework, or just MMDF, is a solution for these 3 problems. The first of this problem is in-out focus image classification. Next, please. And next, please. We started with classic computer vision technique, microscopy focus measures. It's a popular way to use focus measure operators that took a strong place in all digital imaging. Authors consider different focus measure operators, classify them into different groups, measure quality and performance. but unfortunately results on our test data isn't good enough. After that, we worked with blur extent estimation using support vector machine. This approach is just an SVM model that worked with orientated gradients of image. But for our really specific data, this approach isn't wealthy. Next, please. Well, our next point is using deep learning, of course, and as a deep learning baseline model, we used the model based on assessing microscopy image focus quality paper. It's a simple convolution neural network, but with a very interesting loss function. As a loss function, the authors used ranked probability score loss function, and for optimizing the neural network, they used stochastic gradient descent. We improved this model by adding more images augmentations, advanced techniques for preparing data, and using Adam optimizer. The final architecture of the proposed model on a slide. Next slide, please. We use OpenCV for extracting the background of our images, and after that we worked only with images of biological items. As I mentioned above, our model works fine, but our model works with 84 by 84 pixels images, but it's small pieces of source image. That's why we sliced source image to 84 by 84 pixel pieces and processed them. On this slide, you can see the map of predictions. On this map, red squares in focused and green square out focused. Next slide, please. The result of our experiments on this slide were tested on data that not be used during the training. And our test data set is balanced, of course. That's why we can use an accuracy metrics. Next part, please.
The next problem is obtaining image with a higher resolution. For obtaining the image with high resolution, we decided to check ONET, which is familiar in biomedical segmentation, and super resolution convolution neural network, which, because of its simplicity as a baseline. The blue gun is a popular net for deblurring the motion blur. Here it is proposed as solution. Next. On the slide, you can see an architecture of the blue gun generator for obtaining deblurring images, discriminator for distinguish generated and real images. Also, there is additional net which gives a perceptual loss comparing generated images and target. Next. There is a visual comparison of our results of ONET, super resolution CNN, and the blue gun, ranked on 192 pictures with wild blue. Next. ONET and the super resolution CNN images looks like blurred. The blue gun gives picture with clearer lines. Next. Here is the result of comparing the blue gun model on different generated data sets. First column is wild images obtained with the microscope. Second column results obtained on the synthetical blur data set. Third and the fourth mixed wild and synthetic training data set. Next. Here's a larger picture for column if you haven't seen details. Next, the table contains computed PSNR and C metrics. They don't look very good in comparison with blue images, which have high metric values. But I think it's because of some artifacts obtaining by the convolution of blurred image. But if we compare just the blue gun results with these metrics, we can see that adding metric blurred images and training dataset improves metric values. Next.
Okay, and can you hear me? Yes. Okay, the last task was multi-focus image fusion, and the baseline models for this task were classic computer vision technique, wavelet transform algorithm, and the current state-of-the-art model, fusion convolutional neural network. With the aim of improving the quality of fused images, we propose GAN-based model here. So since there is no ground truth image for the task, the no reference quantitative image assessment metrics are widely employed in this case. So we used a pre-trained convolutional neural network that generates image quality predictions well correlated with human perception. And also we used the blind referenceless image spatial quality evaluator. So the standard fused GAN model works in the following way. Firstly, we received multi-focus images as an input to focus detection model that gives us binary segmented masks for each image that contain information about focus regions. After that, we concatenate the input images with their masks, and the result is an input for our generator. And then the discriminator of our model receives the generator output and compares it with ground truth fused image. So here we used, the generator was a UNet-like model that we modified a bit, and the discriminator we took from the PatchGAN model. Igor?
Okay. In the original article, a separate trained neural network was used to generate masks. However, in our implementation, we found it more reasonable to use the modified Harris corner response measure algorithm. You can see an example of its operation on the slide. The model that is trained only on ground truth can smoothly combine the focus parts of the several input images, but some details are lost or blurred. To avoid this effect, we have slightly changed the optimized loss function. Instead of putting into L1 loss ground truth image, we combine the focus parts of input images according to their masks and put the resulting combined image to the loss function. This allows us to get more detailed images. Next.
And here you can see our results. And despite the fact that we managed to achieve qualitative improvements for the image fusion task, as you can see on comparison of considered fusion algorithms, we did not manage to improve the quantitative metrics that we chose for evaluating our models. And the intuition behind that can be that wavelets transform is transform-based algorithm, and that they translate images to another domain, glue them together and reverse the transformation, and therefore image turns out to be smooth with smooth transitions. And contrary, the proposed methods like convolutional neural networks and GAN-based model is a pixel-based approach, so it can still get non-smooth transitions that are invisible to human eye, and the metrics can show that. So the summary of our task is here.